So this is a synthesis from you can do if you've covered alkenes and you've covered alcohols and alkyl halides. So hopefully this is something that's approachable to an organic 1 student. Now, pause the video, write down the compounds, figure out how you would do it, and I'm going to talk about my solution, how I came up with the problem. But what we're going to start out here, this compound on the left, there's a lot of substitutions, and hopefully that's tipping you off to a lot of details about the product, because here's the product. It's 2 fused 6-membered rings with a lot of substitutions on it. So, what do you need to see? Well, this is a pretty esoteric compound here, so that should be your tip-off that there's probably only one way to do this problem, and there's probably a good reason why it's substituted the way it is. So hopefully you can see this. We've got 2 methyls here and 2 methyls here, 2 methyls here and 2 methyls here. So this is actually our starting compound, or at least how it clicks into the final compound. So odds are this is the only thing we had to add in there. And if you're familiar with your alkenes, you're probably going to tip off really quick. We formed a 6-membered ring using a double bond, so this is probably Diels Alder addition. So the Diels Alder reaction, you're going to add ethylene to a diene, and the double bond is going to finish opposite where the ethylene added. So odds are that's our ethylene. So our starting compound here, it's something that looks like this. So here's our diene, and this is our dienophile that attacked it. Now we're still not to this compound, but we've definitely got the right number of carbons, so we're probably not doing carbon addition substitution reactions. So how do we get from there to there? Well, we had to move the double bond outwards, and this is probably the tip-off to you why we have those 2 methyl groups there. It's really there trying to force us or to make these 2 conjugated alkenes possible. So odds are we did an elimination reaction, and we probably did an elimination reaction using either an alcohol or an alkyl halide. Now, ideally you would have used an alkyl halides because they're less likely to do rearrangement reactions. And this is going to be true with something like an alcohol. So we probably started out with an alkyl halide. Sorry, we're going to have to kind of zigzag on the board here. Now again, we could probably also do this by alcohols. Now if we did this type of chemistry, odds are we probably started with them on the secondaries, or the tertiary carbons in this case, because it would have made them more reactive. In principle, we could add the alkyls to the primary carbon, but practicality, you don't want to do that because it's going to force you to go by an SN2 mechanism to get rid of it. So we got 2 options. One option is that we can add a halide. Tell you what, let's not do an X. Let's do Cl. Or another option is that we start out with 2 alcohols right by it. Both of these were accomplished using elimination with a large bulky base. So something like butoxide would do a really good job of eliminating these to give us back to the alkenes, or the dienes. Now, the other nice thing you see with these compounds, and this is probably why we did it this way, there's no hydrogens to eliminate on either of these carbons. They are saturated carbons at this point. So if we're going to do elimination reactions to give us this, there's only one carbon to draw from, which are these 2 methyl groups, which is kind of the tip-off here. That's why these 2 methyl groups are here, is to make this synthesis possible. Now, it is actually possible to take this and convert this to this. We could do something like thionyl chloride. SOCl2 would bring us to this. And ideally, we would actually do this step if we want to guarantee we got the elimination product. There is a chance with this that we would get substitution with a nucleophile. There's also a good chance that we could get rearrangement. But we'll talk about that when we get to the result. The thing is, we can get to either of these if we want to. One option is we can add Cl2. The Cl2 will add across the double bond. We'll get what we want. We do the double elimination, we do the Diels Alder, and we get the final product. The other option here is add K-MnO4, potassium permanganate, and this will give addition across the double bond to give us 2 alcohols. So there are actually 3 synthetic schemes drawn on this board right now. Synthetic scheme 1. We start with this compound, add the Cl2, do the elimination reaction, and go through our Diels Alder synthesis in order to get to the product. And this would actually be a pretty elegant solution. The major drawback being here that you're working with a halogen. So that's the engineer in me saying you don't want to work with halogens unless you have to. Second synthetic scheme. We take our potassium permanganate, form the alcohol, do the elimination, do the Diels Alder, and we're back to our final product. Potential pitfall with this is that we are creating alcohols. There is a chance we can get carbocation rearrangement. There's some things that can go wrong. A third synthetic scheme that you could do. Take your KMNO4, then subsequently react your alcohol with a thionyl chloride, and then go back to the Diels Alder. Advantage of this pathway is that you're going to get the alcohols. You're going to create the alkyl halides, which will be easier to eliminate. You'll have less issues of substitution because the Cl group is less labile than the OH group. And you're still going to go through the Diels Alder. The disadvantage here is that you're doing more steps and you are still introducing halogen to the system. So these are 3 possible answers to the synthetic scheme, but hopefully you kind of saw it. If you're given something that looks weird, like there's a oddly specific compound, not what you're used to naming, something that would make you struggle when you came to naming the compound, look for it in the parent comp, look for it in the final product, and from there start reverse engineering how you get back to it.